Welcome you all. I'm the chair of the physics department here at UC Berkeley, and I'm very pleased to be hosting this panel on state-of-the-art in physics research with some very distinguished guests who are going to be telling you about the state-of-the-art in research. So I'm going to start by introducing my distinguished colleague, Professor Bangfen Zhu, who is my counterpart at Tsinghua University. It's a particular honor. We're both condensed matter physicists. I'm experimental, he's theoretical, but we have so many distinguished speakers at each of our universities that we're both deferring our own research to hear from all these other distinguished guests. So I'll turn it over now to Professor.
First of all, President Gu Bingling from Tsinghua University will give a short opening address for this physics panel.
Ordinary Chancellor Birgeneau, Professor Herman, and Professor Zhu, ladies and gentlemen. In many universities, there are often some departments which have uprooted the culture and spirit of their own university and contributed significantly to the reputation of the university. Those departments are the roots of the university. One of such departments at Tsinghua University is the Department of Physics. Since its founding in 1926, the Department of Physics at Tsinghua has fostered a great number of the outstanding scholars, such as Nobel laureate Chen-Ning and T.D. Lee, and many distinguished scientists who dedicated to development of China. Nowadays, the Department of Physics is still one of the leading departments at Tsinghua University, especially in providing the individualized student training program. The departments of physics at UC Berkeley and at Tsinghua University have a deep relationship, and now both are strong intentions to further extend it. Moreover, both Chancellor Birgeneau and I are working in this field. Today, we come together for mutually interested scientific topics. I sincerely wish our interaction will guide us to further explore the opportunity for closer cooperations, and I believe we can achieve more and better when we put our efforts together. Thank you very much.
First speaker of this panel is Professor Chen-Ning. Professor Chen-Ning is well known both in China and in the United States. I think I don't need to say more to introduce Professor Yang. His name is related with palliative non-conservation and with the Yang-Mills theory, with the Yang-Baxter equation, and Li-Yang theorem. Professor Yang is quite young, although he will be 88 years old this year. As originally planned, the first speaker will be Chancellor Birgeneau, but Professor Yang is scheduled to drive to the lecture hall at 3:45, so Professor Yang will be the first speaker of this panel. Now, Professor Yang gives his talk. The title of his talk is Some Recent Research on Quantum Atom. Welcome.
It is indeed a great pleasure for me to speak again at Berkeley, a campus that I had first visited 63 years ago. I had thought I could boast that among everybody here, I have been at this campus earliest. But now seeing Charlie Towns here, I realize that's not true. I better not make that boast. What I would like to tell you a little bit today is some recent research in cold atoms. Cold atoms was a field that I was already engaged in the 50s and 60s. But at that time, my interest in it was purely theoretical. There were no possible, imaginable experiments to test it. But fortunately, with laser technology and the electric technology, such as this one, it's a chip with some wiring. And if you look at the essence, the red line is a current. And because of that current, there's a cylindrical electric magnetic field. And then with the bias magnetic field, one produces a magnetic field strength 0 region, and that's that little blue line, and that becomes a very good trap for atoms. And with the laser technology, when you go down to something like millidegree absolute, you can trap fermions and bosons. So that becomes a laboratory in which you can do a lot of work experimentally. Theoretically, the problem is, has been shown to be equivalent to a Hamiltonian of this type. The first part is the harmonic oscillator. The second part is a delta function interaction which replaces the two-body interaction for one-dimensional atoms. One-dimensional fermions or bosons in a very narrow tube with a harmonic trapping potential would be describable by such a Hamiltonian. The marvelous thing is that the coupling constant, G, is tunable. With laser technology, you can manipulate with laser and magnetic field. So you can do this, you can study this Hamiltonian for various values of G. Therefore, this becomes a very challenging problem for a theoretician like myself. Now, if you only have the first term without the G delta function term, it's a harmonic oscillator. So every single atom would have an energy written down at the bottom, 1/2 plus n, the thing that we learned in first year quantum mechanics. Now, this Hamiltonian, if you do not have the second term without the G delta function term, this problem is trivially solvable. In fact, it's trivially solvable in 1, 2, or 3 dimensions. On the other hand, if you do not have the harmonic potential, then in the one-dimensional case, it is solvable by what is called Bethe-Ansatz, a very powerful method, which I'll describe in a few more minutes. What my new contribution together with Dr. Ma is that we now want to show that if you have both of them, then the problem is still solvable, and the technology is with both Bethe-Ansatz and the Thomas Fermi method. So if you add to the Bethe-Ansatz method with the ideas of Thomas Fermi, then you can solve the problem with both the delta function interaction and the harmonic trap. So what we want to study is the ground state energy, E0, divided by n squared as a function of G. To familiarize ourselves with this term, let's first look at the case for G equal to 0. Let's first look at the case of this point. This point is G equal to 0. G equal to 0 means there's no delta function interaction, so it's a one-dimensional non-interacting fermions. We talk about the fermion case. Now, if you for the fermion case, because of if it's spin 1/2, there is also, by group theoretical discussions, the irreducible representation. And it is well known that the ground state is an irreducible representation of this type for the Young tableau. And for G equal to 0, that means that half of the particles, the spin up particles, would pile up the harmonic oscillator from the ground state to the n over to 1/2 n excited state. And for the spin down particles, again, you repeat that. So therefore, the total energy is 1/2 plus n. You add that for the lowest n over 2 states. And then you multiply the whole thing by 2, because for the spin up and spin down, you each have that. So you calculate that, you get n squared over 4. So therefore, it means E0 divided by n squared is equal to 1/4. And that's plotted here. So this point we see is 1/4 at the G equal to 0. Next, let's look at the case for G equal to infinity, when you go very far on the right-hand side. When G is equal to infinity, you have n fermions, n over 2 spin up, n over 2 spin down. But if G is equal to infinity, that means the wave function for two particles, whether they have the same spin or different spin, must vanish when the two particles coincide. Even if the two particles do not have the same spin, so that there's no Fermi exclusion, but still, because of the positive G equal to infinity, the wave function has to vanish. That means in that case, it's equivalent to all m particles are behaving a bit like they're all fermions. This is technically called the boson-fermion problem. In other words, for bosons at G equal to plus infinity, it's equivalent to the absolute value of the fermion case. So in other words, we know that when G is equal to positive infinity, you can treat all the n particles, no matter what their spin, as if they are all fermions as far as the energy is concerned. So therefore, the total energy is equal to the summation of n plus 1/2. You sum from, for the lowest n states, not n over 2 states. So therefore, you get n squared over 2. In other words, E0 divided by n squared is equal to 1/2. And that is shown here. So now we have for, when you go to this region, it becomes n over 2. So we now have this point, we have this. It's of course obvious that this plot has to be monotonic, because when G is increasing, the energy has to increase. The ground state energy has to increase by a fundamental theorem. So therefore, we know this region, we know this region. How about this region? Now, for negative G, for large negative G, it forms pairs, because the spin up and the spin down particle would form pairs. Therefore, the m particles would form n over the 2 pairs. Now, each pair, one spin up, one spin down, can easily be shown to have an energy of minus G squared over 4. So the total energy is equal to this expression. Therefore, we get this expression. Now, let us look at this expression. The n dependence, this point does not depend on n. After you've divided n squared, this point does not depend on n, this region does not depend on n, but this becomes 0. That obviously is not quite understandable. So Dr. Ma and I looked at it, and we realized that the right plot is to change the coordinate, the abscissa. Instead of plotting it against g, you should plot it against g divided by square root of n. In that case, this is 1/4, this is 1/2, and this becomes 1/8 times minus this expression squared. So this, after looking at this for a while, we realized that we can make a bold conjecture. The conjecture is that when the system becomes very large, when m becomes infinity and g becomes infinity, both of them, but keeping g over square root of n finite, then the curves approaches a limit, and the limit is approximately of this form. What I want to tell you next is that we have succeeded in proving this. We shall prove this conjecture using the Thomas Fermi method. To understand this proof, let's first look at the case of A, of free particles in a harmonic trap, so one component fermions, m particles. That is a trivial problem because there's no delta function interaction, and we now treat this problem in a trap for, we use the Thomas Fermi method for one component of the fermions. And if we do this, we can ask if this is without mutual interaction, without the delta function interaction. So we have the Thomas Fermi method says that you take a little region here, dx, and you treat the m particles, n is very large. You treat the m particles in this region as if they have a kinetic energy, which is given by this region, and a potential energy, which is given by this. So therefore, you have the maximum kinetic energy in that region plus the potential energy is equal to the total energy, which is at this level, which is equal to it's not m plus 1/2, it's m minus 1/2, but the 1/2 doesn't matter because m is very large. So if you go through the Thomas Fermi method, you would get finally the density as a function of x given by this formula. In other words, the Thomas Fermi method tells you that the density of particles at the point x is given by that. Rho is related to x in an elliptical manner, because if you square that, you get rho squared plus x squared is equal to constant. Now that equation, the relating rho with x, by changing the scale of rho and changing the square of x, becomes the bottom equation, which is this. This is a rho scaled, this is y is x scaled. And that, if you plot, is this curve. So the Thomas Fermi method for the case without delta function interaction, for the limit of g equal to infinity, it gives you this expression, this ellipse. But this problem can be solved rigorously. What I just described is using the Thomas Fermi method. But the problem can be solved rigorously because by brute force calculation, each level gives you the density psi squared. And you sum over all the m particles, you would get this. So let us do this by the computer. The computer for for 5 particles gives you a distribution, density distribution like this. And let's compare that with the ellipse. You see that it's a pretty good fit. If you take m equal to 15, the fit is better. If you take m equal to 55, the fit is even better. What have we learned? We have learned through this exercise that the Thomas Fermi method not only gives an approximate distribution for the density, but it gives the exact limit when m goes to infinity. Thomas Fermi method gives the limit infinite density as m go to infinity, provided you have scaled the variables the way I did. Why? If you think about it, you realize that as m go to infinity, almost all particles have very small wavelengths. Therefore, they are classical particles. Therefore, classical statistical mechanics holds. Therefore, Thomas Fermi method gives the correct limit. So, having learned this, we now apply this idea to the case with a trap. But first, without the potential, without the harmonic potential, but with the delta function. Now, this problem had been rigorously solved with Bether's hypothesis, first by Lieb and Lineker in 1963 for bosons, then in 1965 by myself for the fermions. What was the technology used? The technology is called Bether's hypothesis, which actually is very, very simple if you understand the spirit. And I'm going to spend 5 minutes to tell you what is the fundamental idea of the Bether's ansatz. It is that consider two particles colliding in one dimension, the original momenta being P1 and P2. After the collision, the momenta being P1 prime and P2 prime. Conservation of momentum gives you the first equation. Conservation of energy gives you the second equation. So for given P1, P2, if you regard P1 prime and P2 prime as the unknown variables, you have two equations for two unknowns. So if you look at them, it's algebraic equation. So therefore, you find two solutions. The two solutions are written at the bottom. The first is P1 prime equal to P1, P2 prime equal to P2. The second is the two are switched. P1 prime becomes P2, P2 prime equals P1. The first one is transmission. The second is reflection. In other words, in one dimension, in a collision, you only have transmission or reflection, but no diffraction. That is the key to the success of the Bether's hypothesis. Because if you have now m bodies, P1, P2, Pn, then each collision would just permute, either keep the piece the same or permute the two. So therefore, the totality of the outgoing wave is just n factorial waves, each of which has a momentum distribution which is a permutation of the original one. In other words, the problem becomes an algebraic one. That's the spirit or the key to the Bether's hypothesis. In one dimension, because there's no diffraction, so the Schrödinger equation, which is a partial differential equation in n dimensions, can be reduced to algebraic equation of n factorial size. And that reduction from a Schrödinger equation to an algebraic equation is the key to Bether's ansatz. That also means that Bether's ansatz does not work for 2 dimensions or 3 dimensions, because in 2 or 3 dimensions, there are always diffraction. Okay, so now we know how to do it with Bether's ansatz. And for fermions, Bether's ansatz gives two coupled Fredholm equations exhibited here. I need not explain to you the details. But these equations have been solved by a graduate student in Tsinghua University named Mr. You Yizi. And so we are now going to apply his method. In other words, we go back. Now we have a harmonic trap. And in each dx region, we now regard the problem with delta function interaction. And we apply Mr. Yu's solution to the kinetic energy in this region. And after you do that, you would get the solution to the whole problem. And so we then indeed found that the conjecture is correct. The only thing that we know more is that we now can calculate this red part. The red part is not only proven to exist, but from what I just described, we solved it. Now, for fermions, there is the complication that because of the different symmetry of the irreducible representation, there's another parameter for this kind of a two-column space wave function, Young tableau. There's a parameter. We call this column M. This column M, this column M minus M. N is the total number of particles. So M over N is called psi S. Psi S is equal to 1/2 in this case, is equal to 1/4 in this case, is equal to 0 in this case. So the solution depends on psi. And the solution that we found is exhibited here for all values of psi. The previous one, which I called the red curve, is the lowest one. It's not red in this diagram. The most interesting thing is that the density distribution for the fermions now has a kink for various values of the parameters. We hope that this can be soon experimentally verified. All of these have been, most of it has been published, but there are also additional papers which are about to appear. Once we have understood this idea, we realize that there are many more problems that can be solved. For example, you can use the same idea to treat anharmonic traps. We can use this idea, but with a generalized work on the fermions for higher spin cases and also for bosons. You can study the case of negative G. This is a more challenging problem because for negative G, the Bethes hypothesis and positive G are entirely different. The G equal to 0 is an essential singularity of the mathematical problem. This problem requires a more subtle mathematical treatment. Finite temperature is also solvable because the key is that the beta ansatz, which is usually used for the ground state, has been generalized by myself and my brother in 1969 to finite temperatures, resulting in complicated coupled Fredholm equations. So I believe finite temperature is also solvable. Lastly, a most important thing is a rigorous proof of the Thomas Fermi method. The proof that I had given you is a kind of intuitive proof. I am sure the proof I gave you, the statement I made about the limit being given by the Thomas Fermi method is correct. And the intuition I described in one of the slides. But I think it would be good if we can have a rigorous proof, and I'm working on that. Thank you.
Our next speaker is Professor Charles Towns, UC Berkeley Professor of Physics, Nobel laureate for his work inventing the maser and laser. And he's talking today about his more recent work on astrophysics, measurements of sizes and shapes of old stars and surrounding material.
Well, I'm so pleased that our two universities could do this thing together, and our scholars could come together. I think interaction between scholars and exchange of information and so on is very important in extending our knowledge, and I hope we can go further with all this. I'm going to be talking now about stars, and of course we all know this, we all see the stars up there, but they're so small they're just point sources. Our eyes can't resolve them. We can't see how big they are with our eyes at all. They're just point sources, little tiny bright points. Michelson was the first to measure the size of a star. He did that in the early 1920s, and he more or less invented the method. He put a bar across the 100-inch telescope down on Mount Wilson with two mirrors on either end of about, a bar about 3 meters long. And the light coming from the star to this one, and the star to this one, he joined them. As you join them, the phase of the light changes. As the star moves, the phase of the light changes as it comes to this one and this one, so that when you join them, the two interact and they add and then they subtract. So when you join the two light, the intensity goes up and down, up and down, up and down. And so as the star moves across the sky, it goes up and down, up and down. If the star is big, then it averages out and doesn't go up and down at all. So you measure how much it goes up and down. This gives you a measure of what the size of the star is. Now, a number of people immediately after Michelson tried hard to do the same thing with separate telescopes, but it never worked. That's because the two telescopes would shake with respect to each other and wouldn't stay constant enough. They've got to be constant to a small fraction of a wavelength of light, and nobody could do it. So it just wasn't done for a long time. When lasers came along, however, lasers allow us to control the separation between telescopes and the distance that the light has to travel. And so lasers have made interferometry possible now with two separate telescopes, and it's become a very rapidly growing field. The first projection of mine will show our three telescopes down on Mount Wilson. They're lined up in a row, 4 meters and 8 meters and 12 meters are separated. And they're in trailers, so they can be moved around. We can move them around different positions, different separations. We set them down on concrete pads, and then we use lasers to control their separation very precisely. So these three telescopes can give us a lot of possibilities. One reason for having three telescopes is with three telescopes you can also determine the phase of the fringes going up and down. This tells you whether the star is symmetric or not. So we can measure the asymmetry as well as measuring the size and the shape and so on. And that's what we've been having a great time doing. Now the next slide shows a schematic of two telescopes. We use heterodyne detection, of all things, in the infrared. Wavelength is 11 microns. That's in the mid-infrared. Use heterodyne detection using lasers, local oscillators. As local oscillators. This is the way radio waves are detected, heterodyne detection. We mix the local oscillator, which is labeled LO there, with the light coming from the star, and we get the beat frequency between them. The beat frequency between them then, as this telescope and this telescope, we join them and get the beat frequency between them. And the beat frequency, the intensity then goes up and down and up and down and up and down. And this is one picture of how the intensity goes up and down. We can adjust it. We can adjust it by using a laser. We can adjust it how fast it goes up and down. And it goes up and down, and that's the signal as a function of frequency. Now, one problem with interferometry and with seeing stars accurately is the atmosphere. The atmosphere fluctuates, and the light coming through the atmosphere this way and coming through the atmosphere this way, the relative distance changes because the density of the air changes. And as the density of the air changes, that means the fringes of the signal goes up and down, up and down. And so this other thing over here shows the signal, the fringe, as a function of frequency. But you see it's broad rather than this. This is with exceptionally good atmosphere, very, very pure frequency. That's very unusual. This is with a rather poor atmosphere, and the fringe is spread out. But what we need to do is measure the total energy, so we can integrate under that. Even though it's broad, we can integrate on it and get the total energy, and that tells us how much the signal is going up and down, and therefore how well the star is resolved. Now the next transparency will show actual measurements of Alpha Orionis. That's Betelgeuse. That's the star that Michelson measures. A very bright star in the sky. And this is the spatial frequency on the sky, 10 to the 5th radians. 2 times 10 to the 5th radians, that's about 1 arc second. So this represents a resolution of 1 arc second. And you see the star itself should have, if we see the whole thing is unresolved, it should have a visibility of 1 as it goes up and down 100%. Now, even with this resolution, 1 arc second, we don't see the full energy. In fact, this star, as many old stars are, is surrounded by a region of dust. And that dust emits infrared, And so the star is resolved here completely, and this radiation is due to the dust around the star. And so here we are resolving the dust around the star. As we go to higher and higher spatial resolution, the dust gets resolved, and the visibility goes down and down and down. And that tells us what the shape of the dust distribution around the star is. Now this is spatial resolution in this range. Let me show you spatial resolution in a higher range now. Next one. This is a higher spatial resolution, and here we are resolving the star. The star, and the visibility drops to 0. This is actually visibility squared. It drops to 0 at this distance. That's about 1/20th of an arc second is the resolution. And so we can measure the size of the star, and this is the radius, 27.37 milliarc seconds. That's about a 40th of an arc second. That's the radius, so the size is about a 20th of an arc second, 50 milliarc seconds, or 54 actually. And we can measure it very accurately. Now, Michelson measured it moderately well, but one problem, particularly with these old stars, they have not only dust around them, they have gas. Now, the gas can be very close to the star. The dust doesn't form until 3 or 4 stellar radii out, so you can separate the dust and the star, as we have here. We're seeing the star only. But you can't separate the gas, which is right around the star. And if you have a broad bandwidth, you're looking at a wide range of frequency. You see some gas and some star. You don't know exactly where the star is. We use heterodyne detection in part to resolve that problem. It has a very narrow bandwidth, and we can tune it. We can go on a spectral line, and we can go off a spectral line. We're sure we're seeing the star. We're sure we're seeing the gas. And we know we're seeing the really star, and we can measure it very precisely here. That's sort of the best and most precise measurement that's been made. Now, the next slide will show the size of Alpha Orionis as a function of time. We've measured it over about 15 years. This is 15 years Julian days. There's a number of days times 10 to the 6th. 15 years. And you see it varied from about 56 milliarc seconds down to about 47 milliarc seconds over 15 years. So it's been gradually shrinking. Nobody knew that would happen. It's a very old star. Now, some old stars change a lot and regularly, but this one is a type of old star I thought was pretty constant. But no, sure enough, it's been changing over 15 years. Why, we don't know what's happening, but some instability. What's going to happen next, whether it'll swell up again or continue to get smaller and maybe collapse and explode, who knows? My guess is it'll just stay there for a little while and then maybe swell up a little bit and then change some more, but who knows? And over 15 years, nobody's seen that kind of thing before. However, there are old stars that change regularly and systematically. They change in a time scale of about a year, getting bigger and smaller and bigger and smaller. That's been known for some time. It was first discovered by the Moors, who saw this star up in the sky. It's one of the only variable star one can see by eye. It gets bright and it can be seen, then it fades out and you can't see it anymore. They discovered this. It's called Mira. The next slide shows behavior of, I got the slides wrong. This slide shows the difference between the visibility of a star and the visibility of the gas around it. This is on a water vapor line, and it shows the difference in the radius of the star, which is 54, and the water vapor is a little bigger, 63, or 64 milliarc seconds. So we can see just where the water vapor is. Now the next transparency. That shows the variation in the size of Mira. And this is a function of time. This is about a half a year's time here. You see it goes at a maximum, then it goes down again. This is 3 separate years. And so we can measure the maximum size and how that depends on the brightness. Now, theory, we had theories of them. We thought we could calculate maybe as it gets bigger, it gets cooler. So the light goes down a little bit because it gets cooler even though it's bigger. But if it gets bigger for a while it gets bigger, it gets brighter, then it cools off and then gets weaker, and then it collapses again, gets hotter, gets brighter again. And we can see with this curve, we can see just when is it brightest. It's brightest here about 1/12 of a cycle before its maximum. We can measure its maximum, and it's brightest along about here, about a 12th of a cycle before it gets its biggest size. So this is the first time it's been measured in size. We can see it vary and measure how much it varies. It varies about 30% in size, actually. Now, in addition to stars, we can study the dust. In infrared, we see the dust. We can get on or off spectral lines. The dust is always there, of course, but it's separated from the star, so we can separate them and decide how the dust is distributed and how big the star is. And the next slide will show the visibility curve of a star. This star is called W Higher, which that's not very important, just what it's called, but this is the visibility curve. See, the visibility would be 1 when it's unresolved, and it's more and more resolved, and then resolve it, and the visibility gets down very close to 0. So you're seeing primarily dust and hardly seeing the star at all. The star would not be resolved yet, but yet the visibility is there. The stars are completely hidden by the dust, and we don't see it in visible light. Now using this curve and the phase, as it says how asymmetric it is, we can plot just what the distribution of intensity of dust is as a function of distance back and forth from the star. This is the star, and here's the dust spread around the star, and you see it's a little bit asymmetric, but sort of more or less surrounds the star reasonably. The next transparency shows another star with 2 separate dust shells. Now, that's interesting. These stars can just evaporate material, or they can sort of pulse and blow off material in shells. And you see here, this is a picture of the star, the visibility, over 2 separate years. And this is the curve of distribution of the intensity of the dust, those 2 years. The solid curve is 1 year. You see there's a shell here of dust, peak there, there's another little peak there, and then there's a peak there. So there's 3 separate shells of dust. And now over 1 year we can see them move, and the dash curve shows what it is the next year. So we can see just how fast the dust is expanding around the star. So look at all the detail that can be measured. Now, that's what interferometry does for you. See, otherwise, we don't know much about these stars, but now we can find, wow, they're very active, they're doing a lot of things. We can examine a lot of details, and now hopefully we can understand why they're doing that and what they are, and maybe what our sun will do eventually. The next slide shows the brightest infrared star in the sky. It's called IRC plus 10216. It has that kind of number because it's not seen visibly. There's no light we can get from it because it's so covered with dust. But it's the brightest infrared star in the sky. These are visibility curves, and there's the asymmetry measurement. And now these are 2 different visibility curves, 2 different times. And here's the distribution of the dust. You see how asymmetric it is. And the 2 curves show 2 different years. The dust is moving. Very asymmetric. This funny star, so say the brightest infrared star in the sky, has blown off a lot of material, much more in one direction than another direction. And at various times, you see, there's various shells, bumps here, so on, coming out of it. So it's very active, very crazy, asymmetric, and so on. Now, most of these stars with dust around them are fairly old, and they're active and doing a lot of things. Our sun, fortunately, is very, very stable. If it were making these kind of changes, we would freeze or melt or whatnot, get hotter or colder, and have dust flying at us and whatnot. Our sun, fortunately, is very, very constant. We round just the right kind of star. It's remarkably constant, and we need that badly. But we know as stars get older, they begin to do these kinds of things. When is our sun going to do that? We don't know, but theoretically, we think it won't be misbehaving like this maybe for another 5 billion years. So perhaps we have a little time. Our sun will stay, and we're very fortunate that that's it. You see, new technology tells us a lot of new things. We haven't known these things about stars. Before we could guess them and do theories, say, oh yes, well, we know they're blowing off dust because they're dark, many of them, and they get brighter and darker and so on. We can see them. They must be changing in size. Myra was, at least. That's one we could see. But the details of just how much and just what they're doing, we couldn't know. Now we can begin to tell a lot of detail, examine the stars in great detail, and hopefully understand more and more about how stars behave, and as I say, eventually what our sun will do. Thank you.
Our next speaker is Professor George Smoot, professor of physics here in Berkeley, as well as director of the Berkeley Center for Cosmological Physics, and Nobel laureate for his work on cosmic microwave background precision measurements. And his talk today is Mapping the Universe and Its History.
I want to show you first some very recent data. So this is data we released. Is it possible to get the lights in the front turned down? This is data we released just late March from the Planck satellite. And this is a map of about a 50-degree by 50-degree patch on the sky. And in this patch, you can see the galactic plane very clearly. So this white along here are the stars in the galactic plane. The galactic center is about here. This is a schematic of the satellite. And this is what we call coal dust that's in a beautiful sort of fountain on that. Now, we're far along in mapping the sky. We have, as of March 12th, we have about 85% of the sky mapped, and we'll soon have almost all the sky mapped. But this is picked out because it's a very beautiful area in the sky. Okay, so for a little background, this year is the 4th anniversary of Galileo not only setting us on the part of observing the world and by induction figuring out what's going on, but he made a device to augment the eye, the telescope you see on the right there, and that device was only about a factor of 2 better than the best naked eye. But with that, he was able to make 4 great discoveries: the 4 moons of Jupiter, the phases of Venus, the craters on the moon, and so forth. And but it's the combination of the 2 that have led us on, and we've built now. We've just been improving the telescopes. First optical telescopes, and then second infrared and microwave telescopes and gamma ray telescopes since then, and we're using them to map the universe. So, well, push the wrong button. So here's the latest telescope, 400 years later, and here's one of the early exposures that was done. And this picture is remarkable because when I was young, we had pictures of individual galaxies, but not a field like this. The first thing you should note about this picture is there are only 4 stars in it. This is a star, this is a star, this is a star, and there's a star over here. Everything else in this picture is galaxies, right? And you can recognize some. There's a spiral galaxy, much like the one we live in. But there's over 1,000 galaxies in this picture, which seems like a lot. But if you realize the field of view of Hubble is extremely tiny, it's less than 1/40th the size of the moon. And if you were able to use the Hubble telescope to take these exposures all around the sky, you would see more than 100 billion galaxies. And the reason for that is we can do a census and estimate there's roughly 100 billion stars in our own galaxy. And everywhere we look near a star, we see galaxies behind it. And you can just do a census because we can't do anything else. Okay, so what about mapping the universe? So are we starting out that? So here's the concept if we're doing a cosmic scene investigation. Then when we look out into space, we also look back into time. And so in this picture, we put the Earth here in the center, and we consider looking out to spheres at various distances. And if I look out, like Charlie, to some of the nearest stars, when he takes those pictures, he's getting an image of the stars as they were about 10 years ago. Or if he takes more distant stars in the galaxy, could be 1,000 years or 10,000 years, or in the most distant one, 100,000 years. Well, if you're taking a picture and it takes 100,000 years to develop, things can go on over that time period. But if you look out to the sort of nearest galaxies like Andromeda, it takes light 2 million years to get here. So the image you have Andromeda is really an image of it 2 million years ago. If you have an image of the Earth taken from Andromeda and ask, what does the Earth look like 2 million years ago? Well, the Earth doesn't look so different, but humanity doesn't look so similar because there isn't any. But if you look out the typical galaxies, you're looking out billions of years. And if you look back out as far as you can, which is about 14 billion light years, you look back to a time when the universe was 1,089 times smaller. And at that point, it was also 1,089 times hotter. So it was nearly as hot as the surface of the sun. And you can't look any further because the universe is ionized. And you just get the photosphere of the universe, just like you don't look inside the sun with light. You have to end up using sound waves, which is something for some other talk. So the idea we have is, let me go back to this one. The idea we have is we go and measure on concentric spheres outward from the Earth and look and see what we see. We get an image of what the universe looks like, but at various epochs. Here, right near the beginning of the universe, here a little later, and so on. We can sweep through the history of the universe by just mapping concentric spheres in towards us, towards modern time. So the concept here is we live in a spiral galaxy. We happen to live in a spiral arm in a spiral galaxy, far away from the center. But we can consider spheres around us. And then in nearby spheres, there are some modern developed galaxies. And further out, there are these irregular beginning galaxies. And further out than that will be the cosmic microwave background, the relic radiation from the early stuff. Now, this picture is pretty good picture because the beginning of time is on the outside and the present's on the inside. And there are these tiny fluctuations which I have spent almost 30 years trying to map. And in between, there are all this development of galaxies and things going on. And the only thing bad about this picture is it's not the scale, and there should be 100 billion galaxies and where we can see. Now the universe is bigger than this. This is just all we can see because of light traveled. So here's a brief history of what we've done of looking at that last surface. In 1964, Penzias and Wilson used this telescope, radio telescope, and had they mapped the whole sky, they would have got a map that was extremely uniform, the diffuse glow from the early universe, except for this white line in here, which is our own galaxy, similar to the picture I showed you before. And in 1992, we announced that we have mapped the sky with much more precision. Here's the galaxy saturated, but there are cool regions together and warm regions together. These variations are only about a part in 100,000. So the overwhelming picture of the universe is it's extremely uniform at the beginning, but there are very small variations. And 10 years later, we have this more detailed map where you have the galaxy and more resolution. It's basically the same idea here, but with radio telescope signals to emit higher resolution. You see again the cool regions together, warm regions together, warm regions together, cool regions together. That's signs of things on the scale. And in May of last year, we launched this satellite. And as I said, we're well over 85% of mapping the sky with it. With this data, we've been able to figure out what the state of the art of the universe is. First, that it's 13.7 billion years old. The strange thing is composition is it's only 4%, well, 4.5% of 4.56% of ordinary matter. There's a 23% dark matter and a 73% dark energy, all these new and exotic kinds of things. But we have this precision. So when I told the universe was 1,089 times smaller when that picture was made, that's actually accurate to 1 part in 1,000. But while we were doing these maps, our colleagues have been doing other maps. So here's the Sloan Digital Sky Survey, which has roughly 1 million galaxies in it. So you just take pictures like the Hubble picture, except with a ground-based telescope, throw away the stars, right? Sorry, Charlie. And You then estimate the location in 3 dimensions of each of the galaxies and plot it. As the sky rotates, you take pictures, you get a fan across the sky. So here's the first movie. This shows you the geometry of the scans across the sky, those wedge shapes. And then you can see, once you get used to the wedge shapes, then you can see the structure of where the galaxies are and where they're not. And you see there are large voids, where there are almost no galaxies, and other places where there are clusters and superclusters of galaxies. And this one place, which we call, in honor of our guests, the Great Wall. It's not actually just a line of galaxies, it's a sheet of galaxies. And we think there are more than 1 million galaxies in there. But this is only a 1 million galaxy survey, so we can't get it. So this is primarily a US survey. Here is a fly-through of what is primarily a European survey. And if you notice, we're going pretty fast. Light takes 2 million years to get between galaxies, and but no relativistic effects here. But you can see some of these are spiral galaxies, some of these are elliptical galaxies, and when we have the information, we put that information in there along with the color of the galaxies and so forth. Now we'll go out and swing around, and you can see also the geometry of the survey. You'll see the same wedge shape and the fan across the sky, and you can see the 2 fans from this in the survey. Now this survey is being extended, as is the Sloan Sky Survey. We hope in the next thing, I'm helping with people who are trying the next generation, that we're going to map 5 million galaxies. Here's another slice through the Great Wall. So one of the questions we have is the Great Wall like that? So we do simulations. We start with the typical problem in physics. You start with initial conditions and some equations, and you calculate how the universe should go. And so here is a simulation from Cheng-Pei Ma, if it'll come on, of expanding universe, and then those very light irregularities in the early universe under gravity working for billions of years merging together. Sorry, it's holding up a little bit. My computer's probably doing something else. But let me go back for a second. You'll see the universe is expanding, and yet matter is collapsing. And it's a delicate balance about what's going on. So the next picture I'll show you so you can see the features, not just the expansion, co-moves with the expansion of the universe, so the box stays the same size. And then you can see as it goes on, first hot spots appear, and those hot spots link up in kind of a big web. And they get sharper and sharper until it's not quite as good as a spider web, but it's a fairly sharper web. There are voids in between. So this is what we think is happening over the 14 billion years. We're going for almost perfectly uniform universe to a universe that's fairly sharply defined. So here I'll show you the next one. We're going to go from the large scale down to small scale, zoom in and then zoom back out. So this is a 10 billion particle simulation, right? That's roughly 5 billion light years across, so a good fraction of the size of the visible universe. And as you zoom in, you see the web-like structure, and you see where the filaments come together. You get clusters of galaxies, and here they're going to zoom in on one of the unusual things. This is where many filaments come together, so you get a very large cluster of galaxies. Right? And this is somewhere between 100,000 and 1 million galaxies in this particular simulation. And this simulation has ordinary matter, which shows up as yellow light, and also dark matter. The dark matter makes the frameworks, that what was in the earlier simulation, and the ordinary matter, which interacts well with light, strongly with light, can actually dissipate energy and collapse to form stars and then emit light, whereas the dark matter stays puffed up. So as we're going in closer and closer, eventually you'll see 2 galaxies here, which are about as far apart as us and Andromeda. If we lived in this area, we would see galaxies almost nowhere we looked in the sky. And so when you have this wonderful plan view, I call this the theorist view, or God's view, you get a good idea what the universe looks like. Where if you're an experimentalist, this was done at Max Planck Institute, if you're an experimentalist, you end up flying through the universe. White is where the dark matter is, yellow is what the ordinary matter is. And when you fly through the universe, it's much harder when you're in the middle of something to understand it than when you're out there. So you'll notice the white is puffed up and the ordinary matter has collapsed into the potential wells and formed it. So this is a German simulation. The first one I showed you was American, then there was a Russian, and then this is a German simulation. Now I'll show you a part Korean simulation, starting from early in the universe. So we have a wedge of light coming in, and you'll see it was hot and smooth, and this thing sharpen up. I can remove the label, so you're just looking back billions of years, 13 billion years, looking in. You're looking for this kind of structure to be forming in the universe. So now we're going to map the universe. So we're going to start in the solar system and fly out, and we'll pick up speed. So while we were doing that, some of our galaxies, some of our friends were trying to look at our own galaxy and have mapped the location, 2 different surveys have mapped the location and the brightness of the nearest billion stars or half billion stars. And, but remember, that's about 0.25% of the galaxy, but we pick up speed. Remember, it takes 10 years to get between typical stars, right? So now it gets kind of hazy. You have to paint it in because you only know 0.25% of where the stars are. This is sort of what we think the distribution of the stars in our galaxy look like. So this is the Milky Way. And we're in a local group of galaxies that our galaxy, the Milky Way, and Andromeda are the main constituents of it. But there is on the order of 14, if you're only counting middle-sized and up galaxies, or if you count miniature galaxies, maybe 40 galaxies that make up our little local group. But there's only 2 big ones that really count. And then you go a long way out before you start seeing other galaxies. We just kind of live off in the back, in a little village, Now some galaxies are showing up. And we're picking up speed. Remember, it takes like 2 million years to get between a typical galaxy. And now you'll see some that are red. The sky surveys can't see but the brightest galaxy, so there are these things called large red luminous galaxies and quasars, which you can see at much greater distances. So in the center, you see the typical galaxies. Later on, you see the other galaxies. So I have 2 more movies to show, and then I'm done. Okay, so we're going to zoom out a little further. The white galaxies from the Sloan survey. Then you start seeing the luminous red galaxies and the quasars. So we're kind of taking a census, but a mapping census of the universe. And then you see the cosmic microwave background, which is as far as you can look. So that's how much of the universe we've mapped. You can see near us, we've got a pretty good sample of typical galaxies. Further out, of the brightest galaxies, and then of the quasars, and then we have a good map of near the beginning of the universe, but we've got a lot of work to do in between, right? This is a sample of what the universe looks like. Okay, I think my time is up.
Next speaker is Professor Tipei Li from Tsinghua University. The title of his talk is A Cold and Rigid Universe After Hot Big Bang.
So thanks to George's excellent lecture for mapping the universe evolution. So now we can focus my talk on the debating in the cosmology frontier between 2 groups, our group and with the WMAP mission team. Because in science development, the debate is very useful and very helpful event for science development. And I think it's very interesting. As George's introduction, the WMAP with very high sensitivity and high resolution, accurate resolution, to map the CNB, microwave background fluctuation. And with the WMAP, measured CMB map. They released the power spectrum of the CMB. And from the power spectrum, they can release the best fit cosmological parameters. This is very important, with very high precision. For example, for the universe composition, there's a dark energy fraction, dark matter fraction, and so on. And this is one great achievement of first from Kobe and then mainly from WMAP. And another WMAP is released some very interesting and very strange fact. One of the axis of evil. For the very large, most large angular scales, the WMAP found the CMB fluctuation, so-called quadrupole or octupole. And the quadrupole, the direction of quadrupole, and octupole is very alignment. This is very strange fact, because according to for a stochastic fluctuation, the different scales, there's a completely independent fluctuation. So the two large-scale fluctuation components have the same direction. It's a very strange thing. And the more strange is the direction closely related to the solar system direction. This is the north of the solar system, and this is south pole. And this is a more strange thing. It's harder to image at the Big Bang. Now the universe has now, more than a billion years ago, there is a solar system, and now its direction. So it's very strange one. And this is not consistent with Kobe's result. This is quadrupole from Kobe. You can see the Kobe is there's a hot spot and a cold spot is something just a random fluctuation without any arrangement with the solar system. So, and we found the WMAP exposure because WMAP is not uniformly scanned to the sky. Some place the observation number is very high, and some place is very low. And this is the exposure pattern of WMAP. And this just similar with the quadrupole direction. So we guess, we believe this axis of evil not comes from the cosmology, just come from the instrumentation and the observation effect. But it's very strange. So many experiments and so many cosmologists believe this is a cosmology singular. So about 7 years ago, the WMAP first published their first result, released this result. We just don't believe it. So we make a decision. One of my PhD students, Mr. Liu, and with me were together to make a reanalysis the WMAP data. It's not a very easy task anyway. Thanks for the NASA and WMAP team, they make the raw data of WMAP publicly available. It's very, very helpful for us. So we can get the raw data of WMAP through internet. So we can do our job. Now we construct our pipeline, our software package completely independent with WMAP team because we don't believe their result. We have to do our self work independently. So this is WMAP group released map. This is our map from the same raw data, but with different software. And this is the difference of the two maps. So you can see there's a significant difference. And it's very interesting. This difference is just similar with the WMAP quadruple. As our map, the quadruple is nearly to 0. We have can't see the quadruple signature from our map. So it's most possibly the WMAP quadruple is completely artificial origin. And from our map, we can derive the power spectrum. Also, significant difference with WMAP release. So we can get a new cosmological parameters from our map. So there is a huge, significant change of cosmological parameters. For example, for the composition of the universe and the dark energy fraction from the 3/4 decrease to 2/3 is a significant down, and so on. And the dark matter increase accordingly very much. So, of course, our result published on the website, there's a heated discussion and debating within the 1 or 2 years recently. And for example, for the Cosmic Coffee Forum, is a famous forum for cosmology study, and for the science blogs, and so on, there's a heated discussion and debating on our result. For example, from the website, we can some comments for our result. And say the WMAP team has some of the best data analysis list in the world. And this is a very large group. And for many years, hard work. And now there's a couple of guys in China who redid the analysis. And they said there is an inconsistency in WMAP release. So this is a very strange thing. It's hard to believe, anyway. And another, I think this is a joke, just as a Chinese building the cosmology too loud. It's just a joke. It's funny. But I feel it's not, unfortunately, now some people, I think some astronomers like to use the voting democracy to solve the academic issues and related to the academic debating related to countries or nations. This is not a good thing. Well, if the CMB and the result significantly changed, there's a very serious consequence for cosmology study. Because CMB is a connection between the very early universe and the dark age for the large-scale contraction of the observable universe. So if this result change a lot now to the two directions have this also important major change. So for example, for the dark age, one of the netless say in the website, and the other parameters is more important because for many years, many works based on WMAP data must be redone. So jobs for Gales and Boas, I suppose. So this is quite a lot works have to be done again. And for the very early universe, another people say maybe the series is now it's time to look about the new revolutionary physics. Now, for a long time, we have not get the WMAP team a formal response for our argument. And we just have, from the website, have two response from WMAP team. For a WMAP team member in a report in the reference, say the WMAP team insists their result is correct, no problem. And another we found from a Chinese PBS of a Chinese university. He said this morning the WMAP principal investigator said at least two other independent groups verified the WMAP results, starting from the raw data, just like we do. So either three different groups did the same thing wrong, or these guys screwed up. And it's just like, so this case is 3-1 by voting. Okay, so now, just for within 1 or 2 months, the situation have a dramatic change. We finally found how and why WMAP release is wrong. Firstly, we have not enough time to give a detail. Now, just leave just noise, white noise. So if the residual TOD, we give a map. The map just a flat, no singular. It's okay. Our result satisfies this condition. But a WMAP result have a very noise, structured, singular, and so on. And this noise left in the WMAP map is just the control pole they observed. So, and the difference of the two maps also just equal to the control pole. So we can definitely say the WMAP map is a dirty one, and with a noise just like the control pole. So because for a long time we have no. This year, we published it in the website, okay, call for white readers to repeat our test. To see the, just
Yeah, just
No time.
And last month, we get the very interesting. This is the temperature of the model. And from Cobalt or WMAP, you can't see this CMB. You see this picture. There's a very strong dipole comes from the satellite moving relative to the CMB. And the dipole singular is very strong, 10 or 20 times strong than CMB. So we have to subtract the dipole, then can get the CMB picture. And we found in the WMAP software, there's a mistake, an error, very small mistake for the satellite, the antenna's direction, with the error about several arc-minute. It's very small. It's negligible for the map. But you calculate for each observation for the dipole direction, because the dipole is very strong compared with the CMB. So a very small error in the direction cause the dipole, change the dipole amplitude about 10 to 20 microkelvin. It's just comparable with the CMB. So this is a very serious effect on CMB temperature, not on the map. And now we found the two software, the difference of the direction of the antenna. We just use the difference to make an image. We get this result. So in this procedure, without use any CMB map, just use the altitude error, we can exactly produce the quadruple map. So it is a definite evidence that the WMAP released quadruple is the noise. It's not the CMB singular. That is our latest. Okay. So now, just simply here, this safety law is a website. European cosmology. So I think now we can vote on the way maybe we can. Of course, well, we have a lot of time. So there's a very interesting effect our result on the very early university. Maybe it means finally we found after the bang and during the inflation period and before the record phase of war, the comfortable zero comfortable views we observed a very cold and really and not very cold, very low and very hot, really without any this is very interesting for every physicist, I think. And okay, so I have to finish it. And but I think this is important. The Tamilet is very nice, very good eating, and has a great achievement for the world. I think our is an influence to make Tamilet without more beautiful. This is one. Another is, and they disputed our group with Tamilet is very favorable for us because in China, in Tsinghua, we are going to contract and Chinese first topological center partnership for the education. And we will launch it within half a year. And this telescope, compared with NASA and
talk. We're going to cut other people off. So thank you very much. The next speaker is our Chancellor, who I'm very proud to say is also a distinguished member of the physics department, where he's continuing to do his research in a rather impressive way, given that all of his other tasks. So his talk today is on high-temperature superconductors, a surprising development.
This is work we've been doing here in the physics department and up at LBL. I think many of you know this is a very famous graph. This one was produced by Bertrand Batlogg, which is the temperature of transition to superconductivity, beginning with this famous discovery by Kamerlingh Onnes in his lab in Holland of superconductivity in the metal mercury. And they were looking at mercury because they were interested in what happens when a metal goes from the liquid to the solid state, and mercury was a very nice way to do that. And then the graduate student, and then confirmed by Kamerlingh Onnes, discovered that at low temperatures, magically all of the resistance went away, and therefore it's called a superconductor. And over a very long period of time, covering many decades, gradually the superconducting transition temperature was increased up to about 20 degrees Kelvin. And then in 1986, an extraordinary discovery was made, which I'll remind you of. We've been working on this general problem of superconductivity at high temperatures in my group here at Berkeley and up at the lab. And these are a set of people. I might say that we just are gaining in our group a brilliant young scientist from Tsinghua by the name of Jun Zhao, who has been offered a Miller Fellowship and is going to join our research group in July. And so I'm going to talk very briefly, about 3 minutes each, on each of these subjects, and then show you these new materials, which I think are quite extraordinary. This was the beginning in the field of superconductivity. That's Kamerlingh Onnes' lab. There's Kamerlingh Onnes on the right, and who got the Nobel Prize, actually not for discovering superconductivity, but for liquefying helium. But the single most important discovery from that, besides, was both superfluidity in helium and also superconductivity. And those show his original data, which were taken in 1911, and he got the Nobel Prize in 1913. Then a really extraordinary thing happened in 1986, in which two Swiss physicists, Alex Müller and George Bednorz, discovered superconductivity in some really surprising materials, which were perovskites, really ceramic materials, based on which were laminar lanthanum copper oxide. This was then extended to materials. The most famous is yttrium barium copper oxide, which again is composed of, is a copper oxide material, but now with the very important feature that superconductivity occurs at somewhere above liquid nitrogen temperature. So there was a lot of excitement because people thought there would be lots of applications, which indeed there are. It also was clear as soon as one realized that the superconductivity was occurring at such extraordinary temperatures that this had to involve quite new physics. But the physics has turned out to be far beyond anything any of us could have imagined, in fact. And this is the material which has the highest transition temperature, which is, instead of lanthanum copper oxide, it's mercury copper oxide with a little bit of barium and calcium mixed in. And under pressure, this material conducts electricity perfectly at all temperatures below 168 Kelvin, which is truly extraordinary, compared to the original 4.1 degrees or 4.2 degrees of mercury as discovered by Kamerlingh Onnes. Amazingly, the physics of this is still not mastered. But what we have discovered, we, countless people, discovered is that all of the high temperature superconductors until 2 years ago had this feature that you had layers of copper oxide which were well protected from each other. So that's two-dimensional physics. And the essence is that the copper oxide layers needed to be essentially perfect, and you did all of the doping via layers which are in between. In fact, almost all of us agree that if we could simply solve the physics of a single sheet of copper oxide, we could solve the problem of high temperature superconductivity. But there's one extraordinary feature here, which in the brief time we have, I will not dwell on, which is that each of the copper atoms in the insulating state at least has a spin. But it was believed up until this discovery that magnetism and superconductivity were completely incompatible. And then we find that the highest temperature superconductors, rather than excluding magnetism entirely, seem to have magnetism present at the atomic level. After a lot of work, people then ended up systematically looking at the copper oxide materials and discovered a very elaborate phase diagram in which at zero doping, you have a magnetic insulator with a very high transition temperature. With only a few carriers, the bulk magnetism goes away. You enter into another peculiar magnetic state called a spin glass. And then at a magic concentration of 5.5% carriers, the material becomes a superconductor of D wave rather than conventional S wave symmetry. So this has led to an extraordinary amount of work, and I want to make this very brief, so I'm not going to dwell on it. My favorite model is one in which the charge carriers organize themselves into chains, basically, with the charge carriers going along these sort of rivers of charge and with the magnetic regions in between them. It's believed by many people that magnetic excitations mediate the superconductivity, by many, but by no means all. For solid-state physicists, this is what the dispersion relation looks like, which is that at very low energies, you have fluctuations which look like the stripes, charge stripes, moving against each other. There's a crossover point, and at high energies, you recover the excitations of the insulator. So you have excitations which are characteristic of a doped insulator at low energies and of the insulator at high energies. So this then led many of us to believe that the physics of high temperature superconductivity was the physics of what are called doped mod insulators. That is, you take a very peculiar magnetic insulator, you dope it, and it becomes a superconductor. And this became basically our Bible. Well, a very shocking thing happened just 2 years ago, actually exactly 2 years and 2 months ago, in which a researcher in Japan who was looking at some iron arsenide materials with a very different motivation. He was not at all looking for superconductivity, which is in contrast to Bednorz and Mueller, who were actually searching for high temperature superconductors. So this person was looking for very different kinds of properties. Then there's been an avalanche of material overwhelmingly done in China. So this is a problem to date which has been completely and entirely dominated by Chinese investigators at universities like Tsinghua, Chinese Academy of Sciences, et cetera. And they've discovered now a whole new family of high temperature superconductors, all based on sheets of iron arsenide. And there has been some amount of work done in the US, but it turns out that work is dominated by investigators in US universities, usually who started out in Chinese universities and still have some friends back in China who would send them materials. So it's been a very interesting development and very surprising. This is our own work on the phase diagram of one of them, and I'll only point out that you get a magnetic state and then a superconducting state, and the topology of the phase diagram is closely similar to that of the copper oxides. So this implies, and then this shows in a particular material also, phase diagram which is again closely similar. This is not our work, this is work again done by a Chinese group, except for one real peculiarity, which is you can see right near the crossover point, there's a range in which the material has a structural phase transition, a magnetic phase transition, and a superconducting phase transition. And it appears as if the electrons are participating in all of these three phases simultaneously. But generally, we see that, again, you have competing phases with magnetism competing with superconductivity. And I'm going to skip through our own work because I want to give time for some other people to talk. Okay. And so let me just say why this is such a surprising development. So first of all, the parent materials, rather than being insulators, and so much of the research on the copper oxides has been, theoretical research has been looking at the theory of dope mod insulators. These are metals to begin with. All the data I skipped show that in the iron pnictides, the magnetic and structural transitions are very intimately connected in a way they're not in other superconductors of any sort. So that feature is unique. Like the copper oxides, it's found that antiferromagnetism and superconductivity compete. Finally, the phase diagrams, even though these are completely different materials, they're somewhat more three-dimensional. They're semi-metals in the undoped phase, and they're based on iron arsenides rather than copper oxides. The phase diagrams are remarkably similar. So this then leads to a question, which is that for those of us who have been working sort of on the microscopic details of the copper oxides, focusing on copper oxygen charge transfer, et cetera, whether or not we were seeing the trees and not the forest, and raises the issue of whether or not there is a universal model for these highly correlated electron systems in which the details are remarkably unimportant, but in which the essential feature is that you have competing antiferromagnetic and superconducting phases. One of the other side comments I might make, which is relevant to the next two talks, is that if you look at almost all of the really important developments, including at the most fundamental level of condensed matter physics in the last several decades, every one of them has originated either from the discovery of new materials or the discovery of new properties of old materials, and demonstrates the symbiosis between materials research generally and discovering new phenomena in physics, which very often, like both of these, were entirely unanticipated. Thank you.
Next speaker is Professor Shoushan Fan. He talked about carbon nanotube from materials to applications.
The last 5 talks are all about a big problem in physics. Now I try to move to small materials, carbon nanotubes. I'm the director of Tsinghua Foxconn Nanotechnology Research Center. This is an industry-supported nano center. We are an open platform for nano research at Tsinghua University, but we also try to build a bridge between university and the industry. And main interest in our center is focused on IT-based nanotechnology, especially on carbon nanotubes. And carbon nanotube has been hot materials since it was discovered in 1991 by Dr. Ijima. Why carbon nanotubes are so attractive? I think it is very good materials. It's ideal materials for one-dimensional physics. And it has very unique properties, and it has been impacting, have a lot of potential applications. Our research began synthesis of carbon nanotubes. There are 3 methods to make carbon nanotubes. And here is a picture for on the TEM for carbon nanotubes. We can imagine it is very difficult by using this kind of material to make a real device. There are a lot of challenges problem to be overcome to make a real device based on carbon nanotubes. We need to develop a method to control the synthesis of carbon nanotubes. We began from making carbon nanotubes use CVD method because it's a low temperature method, also compatible with IC processing. The first step, we try to grow nanotube on a silicon wafer. And we can grow a very regular nanotubes. But when you focus the in, you find that the nanotube inside is not very regular. It's still a little bit of mess. And how to improve the quality of carbon nanotubes inside the array? we developed two tricks to study the growth mechanism of the carbon nanotubes. And the first method is to use carbon isotope labeling method. We use C12 and C13 gas, carbon hydrogen gas, try to grow the junction of C12 and C13. Then we use micro-Raman to mapping the nanotube arrays to find where is C12, where is C13. Then we get, Then we can see how the nanotube grows from the nanocatalyst. And the second trick is when the nanotube grows, we interrupt the growth, we leave a mark on the arrays. We design a small chamber. We introduce a carbon hydrogen gas to grow nanotube and introduce another post-argon gas to stop the growth by second. Then we can make a mark. According to this mark, you can get the growth rate of carbon nanotube arrays and use this data to study growth mechanism. Based on understanding growth mechanism, we can get we call the super-aligned nanotubes. Up picture is ordinary arrays, and down one is a super-aligned carbon nanotube arrays. You found the nanotube inside the array is well aligned, and the surface of the nanotube is very clear to form some bundle. Based on this super-aligned arrays, we find a method to spin the ions and the films from super-aligned arrays. Here's a film you can see. This is a carbon nanotube array on silicon substrate. If you pick up the carbon nanotube ions, it can continuously to transform the carbon nanotube arrays to the very long ions. From this picture, you can get how the nanotube arrays around 100 micron higher form a very long nanotube ions. And right now, we can grow the super-aligned carbon nanotube arrays on 8-inch wafers. It can continuously transform into a very long, transparent carbon nanotube films. And if the film goes through a liquid drop, it can shrink into a very thin carbon nanotube ions. Right now, we have a technology to mass produce carbon nanotube arrays and the film. I give you a figure. From one 8-inch array, you can get 200-meter-long films. This film is transparent, conducting, polarized, porous, and flexible. I think this material has a lot of applications. Following, I will give some example how we use this carbon nanotube ions and carbon nanotube films. The first example is we use carbon nanotube arrays to make the carbon nanotube and the polymer materials to use it as a thermal interface between the heat sink and the computer chip. And the next one, we use carbon nanotube ions to replace copper to make a microcoaxial cable. And also based on the field emission properties, we make a field emission carbon nanotube device for both luminescence and flat panel display. This is a small uses. We use a carbon nanotube film to make a TEM grade. You can get a lot of nano holes. There are a lot of chances you can put your nanoparticle, big molecular materials, and nanowires on a grid. You get a lot of chance to get a good picture for a TEM picture. And also, you can use polarized properties of CNT film. It's a very good UV polarizer. And also, radiation from the carbon nanotube heater is a polarized light. And I skipped this one. Also, carbon nanotube thin film is transparent, and transmission is around 90%. And we use it to make a touch panel. This touch panel is replace India tin oxide. It's a commonly used for nowadays for commercial touch panel. I have a first carbon nanotube touch panel sample. This is the first mobile for use our carbon nanotube sample. And we have a mass production line for this carbon nanotube touch panel. We also found that you put a carbon nanotube thin film on 2 electrodes. If you apply for an audio signal, it is a very good speaker, loud speaker. This is a device. And you just put one layer of carbon nanotube film and put on 2 electrodes. It's a very good speaker. Also, this is based on the principle of thermal acoustic properties of carbon nanotube. Because the mass of carbon nanotube film is very small, it responds to the current is very fast. Also, this carbon nanotube loudspeaker is flexible and also is stretchable. You can stretch it. And the music is still same. And here is a real sample. We use a carbon nanotube film to get a speaker. That is a very famous Chinese song. Just do it. And I get a conclusion. The carbon nanotube is a very unique materials. It offers a lot of opportunity for both academic and industry. We developed some method for mass production and control the growth. We try to find some application, but I think for large-scale industrial application is still on the way. Need a lot of efforts from both academic and the industry. Thank you.
Last speaker from Tsinghua is Professor Qukun Xue. The title of his talk is Molecular Beam Epitaxy Growth and the Novel Properties of a Topological Insulator Thin Film.
So I'm inspired by the Chancellor's talk. I come here to find some collaborator at Berkeley by providing some good sample of topological insulator thin film. For the time being, we are one of the very few group grew the topological insulator thin film of bismuth telluride and bismuth cellulite. So it's always dangerous to give a talk in front of a big professor, particularly Chancellor present. But I'm doing that. I'm lose my job after today's talk. Okay. So the topological insulator was mainly experiment developed in the last 2 years. So I just attended the American Physical Society March meeting about 2 weeks ago in Portland. Even on the first day, Monday, we had 3 symposia on the topological insulator. So here, the Professor Joe Moore, if I pronounce correctly, gave the invited talk. I was also there, but in a different session. Topological insulator was shown have some greater potential in the future information technology, such as spintronics, quantum computing, and also those materials host many fascinating property like the magnetic monopole, Majorana fermion. If you bring the topological insulator film and a superconducting film together, you may find this Majorana bound states in the vortex of the semiconductor. And also, they are very much related to this study of dark matter. I don't know anything, but if you read this paper by this Nobel Prize laureate, can be studied with this topological insulator. So this is, I really don't know. But in any case, this topological insulator appear a very exciting materials to study with. So actually, those materials can cover the many aspects in physics, magnetism, spintronics, even the superconductivity, and also in the material science, probably in the very near future in the microelectronics. And for the recent review paper, please find these 3 by Professor Zhang Shouchen at Stanford University, Professor John Moore, I think he is in the audience, and also Professor Hassan and Ken. They are basically the main player or the pioneer of the topological insulator. So in terms of these very exciting materials, the first I like to give you some idea what is this topological insulator. Also, I just point, because it is a time limited time, I just give a very important but outstanding issue in the study of the topological insulator. I show some of the good film which the Berkeley colleague can use. I will send them to you. We have to actually discussing after my talk, after this session. So in nature, we have 2 different materials. One is a conductor, another, insulator. This is the classification is very simple. If you look at the materials in a different way, we have the different thing here. So I show you some daily stuff, orange and donuts. They belong to the same type of them stuff, okay, food that we can eat. Also there are here some of the different, this is the bowl, the dishes, and the tableware, also this coffee cup. But these belong to the 2 of the same kind of materials. But in the language of the topology, orange is completely different from these donuts. Actually, rather, the donuts can belong to the same catalog of this cup as shown here. So we have the different classification in terms of this topology. Basically, topological insulator can be understood in a similar way. This is an ordinary normal insulator. We have this conducting band and a valence band. Because this is a very strong spin orbital coupling, there is a band twisting in the case of topological insulator. Because of this band twisting, within this gap, you have this linearly dispersed surface states. So because the linear dispersion give you this Dirac band structure. In any case, in the gap, we have this metallic surface states. So due to the formation of these Dirac surface states, then the surface of this topological insulator, even it's the insulator, the surface become conductive. Okay? So now we have the third or the new type of materials in addition to the conductor and the insulator. So the topological insulator, they sort of. And where the bulk is insulating, but on the surface, because this metallic, the surface Dirac band structure, this surface become conductive. Just like you caught this ball with this gourd. So this is give you some idea what is topological insulator. Actually, this kind of property really comes from this relativity effect proposed by this giant science giant Einstein. One of the very important but the outstanding issue in the study of topological insulator is the materials, quality of the materials. Most of the study was done with this single crystal, prepared by the Professor Fisher in Stanford, bismuth telluride, and also another group, Kawa and Princeton bismuth selenide. So Professor Shen at Stanford used the apex, demonstrate this, you see this, we have this Dirac, as I mentioned in the introduction. And also for these materials, the electronic structure can behave very, like this Dirac. So this is great experiment. If you look at the detail of this band structure, in addition to this Dirac, the Fermi energy, this is the Fermi energy, this is the Fermi energy. So around this Fermi energy, we also observe the contribution from the bulk, the electron pocket from the bulk. Means the Fermi energy of these materials in this single crystal and this single crystal located at this conductive band. So if you measure the property of these materials, you should expect the contribution from the bulk. So what we need, we have to shift down this Fermi energy from the conductive band to the gap of the insulator. Now, only cross this Dirac surface states. If you measure the materials property with this kind of structure, you expect the main contribution come from this surface Dirac or this, this topological state. So this is really we are working on the materials for this kind of the band structure. And my research is in my group at Tsinghua University. This is some schematic of our machine. We combine the molecular beam epitaxy, MB, and FTM, and also APEC together in the same system. So with this system, we can prepare the materials by the MB with atomic level control. Then we can study the property of the nanostructure film prepared by MB with the FTM and APEX in situ. So everything done in the same ultra-high vacuum system. So this is the picture of this MB, FTM, APEX combined system. We also have another system, MB combined low temperature FTM, so operated at a very low temperature, 400 millikelvin, and up to the magnetic field of 11 Tesla. So this is show you the performance of this machine by measuring this superconducting gap. And we know the resolution of this machine is less than 0.1 millieV. So which allowed to detect the single spin states or the single charge states. Even relative to the Chancellor's talk, we observed the superconductivity transition for single atomic layer metal thin film. So the Chancellor mentioned high TC, but the transition temperature here is quite low. But now the materials only consider single atomic layer. And I look at the website of the Berkeley physics. I found many possible collaborators, particularly 2 or 3 years ago, Professor Chiu, we already did some of the we already collaborated together in the terms of this topological insulator, Professor Donghai Li and John Moore. I think we can really discuss and find some of the collaboration on this exchange program. And this shows you some of the materials we prepared. We used this MB. We realized layer by layer growth of both two materials, as evidenced by this electron diffraction oscillation real time during the growth. So one cycle of the oscillation in this figure graph corresponds to the growth of the single atomic layer. Another cycle, you will see growth of another layer. If you continue like this, you will get this atomic layer by atomic layer growth. And this is the evidence demonstration of this good morphology you expect from the layer by layer. So you see this, the film, this is the STM image, 200 nanometer by 200 nanometer. Over this range, you only see 1 to 3 atomic steps, means our film is really atomically flat. If you zoom in, look at the detail here, you see this, a single atom very orderly arranged together. So here, the bright feature corresponds to a single, I think in this case, the selenium atom. And if you measure the band structure in situ by the apex, you see this Dirac-Kahn structure. You also see this Fermi energy is located in the gap, not the conduction band, as I already pointed out in the earlier part of my talk. Same thing we did for the bismuth telluride, very flat film and atomically ordered structure. Again, we measure the band structure by apex. You see this Dirac-Kahn, again, this Fermi energy is only across this surface Dirac-Kahn within the gap. So very good for the further study. And with this high quality film, we did the three, I think, a very exciting experiment. First, by the STM observation of absence band scattering, we demonstrated that the topological state is indeed protected by this time reversal symmetry. Second, since this is a two-dimensional system, if you apply the magnetic field, you should observe this quantization. So we did that. Also, by combining this, superconducting thin film with topological thin film, you may study this Majorana states and so on. I just show you the first example. On the surface of the bismuth telluride, we see this standing wave caused by this silver single atom impurity. So you see at the different energy, you see the different pattern. By the Fourier transformation of this standing wave, we know we only have the scattering along this gamma m direction. So you have the support gamma m, you have another gamma m, but along this gamma k direction, there is no scattering. This is, without going into detail, I just want to point out this observation indicates the band scattering in the surface of the topological insulator is missing. This is a property of the time reversal symmetry. And like the graphene, these two-dimensional materials, now we only have the surface states. If you apply the magnetic field, we expect this Landau quantization of the Dirac fermion. This is just last year's data on the graphene using the STM. So this is our film schematic shown here. We are applying magnetic field in the direction perpendicular to the surface. Then with increasing the magnetic field, you see this kind of individual peak. This peak corresponds to the Landau level Landau level. This is just zoom in from this 10 Tesla case. You see clearly the individual Landau level developed from this topological surface states. And maybe we can collaborate with the Chancellor's group. We can make the superconducting film on top of the topological insulator by using the molecular beam epitaxy. He also mentioned this, ion-based superconductor. So we already we already obtained quite good materials of ion selenide, on top of the graphene. So this is the large scale image. This atomic resolved image. You can see there is very few defects. If you measure the superconducting gap at the function of temperature, you know they are superconducting. So we can really work together if you are interested. And if we apply the magnetic field, we expect this formation of the vortex. If the vortex interact with the topological surface states, that's the we may see this Marjorie states proposed more than 70 years ago, I think. So this is basically form the basis for the so-called the quantum computation. And I think I have to stop my talk here. By using this MB technique, we can really prepare atomically flat thin film on many different substrates like silicon, gallium arsenide, silicon carbide, even some metal surfaces. So this is, created a very rich platform for the study of a topological insulator. So probably, so now, and this electron in the silicon chip already very crowded. So in the future, by using this topological insulator, I hope we can solve the problem as schematic shown here. With that, I would thank you very much.
Okay, so we're going from the tiny to the enormous, and our last speaker is Professor Marjorie Shapiro, who is going to be telling us searching for new physics with the Large Hadron Collider, and we're very excited that she could even be here with us since they're busy actually colliding things now.
So I'm sure most of you have heard that last Tuesday, the LHC Large Hadron Collider in Geneva, Switzerland, had its first high-energy collisions, the beginning of the high-energy run. The collision energy was 7 TeV. That's 3.5 times higher than any collisions that had been made at an accelerator previously. And you can see on the right-hand side of my opening page some event displays that were taken during the first day of running. After having some celebrations, this is the culmination of a building effort that took on order 15 years. People have rolled up their sleeves and gotten down to work. And in fact, in the week that's followed, we've actually written 7 million events to tape. So that tells you that for the start of a run, things are going pretty well, and we're all amazingly excited about it. Now, that being said, this is really only the very beginning of what we intend to see coming out of the LHC. At the present time, the luminosity, which is a measure both of the beam intensity and how well one can focus them to collide on top of each other, is 10 to the 27th. That's 5 orders of magnitude less than what we expect for this 2-year run at 7 TeV. And the energy of 7 TeV is actually half of what we ultimately expect to get out of the LHC. The 14 TeV energy won't occur until after a shutdown that should finish at the end of 2012. The scientific program for the LHC is something we expect to last a minimum of 20 years. The Fermilab Tevatron, which was the last high-energy machine, started taking data in 1987 and is still going strong. And we would expect the physics program of the LHC to be similar in terms of length. So again, this is just the start of a very long exercise. And what I'd like to do today is I'd like to tell you a little bit about what the goals of the LHC experiments are, what we might find, and when we might find it. And I'll say right at the start, this talk is really aimed at the non-expert. So I apologize for the people in the audience who could probably give this talk as well as I can. Okay, so as you all know, particle physics is the study of the constituents of matter and the forces that act on them. In the standard model, we believe there are 3 generations of quarks and 3 generations of leptons, and they work together through the mediation of the force-carrying particles. Now, although the techniques we use now seem very high-tech, the actual philosophy of what we're doing is rather old. There's really nothing here that wasn't first done by Rutherford in 1910. The way Rutherford first discovered that the atom had a hard core is he bashed something into the atom and watched it scatter off it. And the idea is by studying the recoil, you can understand what's happening inside the processes you're looking at. So paradigm number one for the particle physicist is to study the smallest substructure. We need to use high energy probes. And the smaller the structure we want to look at, the higher the energy of the probes we need. And that means we have to accelerate particles to high energy. And in order to get the most bang for our bucks, we collide them head on so all of the energy can actually go into that collision rather than the kinetic energy of the things we put out. Now, antimatter and antimatter can be created at high energy, and the basic idea here is just Einstein's equals mc squared. So that means that if we have high enough energy collisions, we can produce new particles of high mass by turning that energy into the particles. And the creation of destruction and destruction of these particles occurs all the time in nature, and we're basically going to follow the same idea here at the collider. So paradigm number two for us is that high energy collisions allow us to create massive particles, and these massive particles are unstable. They decay typically within our detector, and we look at them by looking at their decay products. Okay. The third thing I want to point out is that particle physics and cosmology in recent years have become very much tied together. We've heard two beautiful talks today about the state of cosmology, and so I'm not going to begin to tell you that. You've heard much more about it than I can. But the important thing is that one of the things we can do is by looking at these high energy collisions, we can learn about the early universe. So I've taken a slide from the particle data group that shows us how, as a function of time, we have different eras in the creation of the universe. And if you look at the era that we can actually study using the LHC, you can see it's about 10 to the minus 10th seconds. So not yet as close to the Big Bang as we would like, but certainly closer than we've gotten before, and a very interesting era because it's the era where we see a real phase change in what's happening. It's the era where the particles gain their mass and really change their character. Okay, so what's the tool that we're going to use in order to do this? Well, I already told you it's the LHC, and what you can see on the right-hand side here is an aerial picture of the Large Hadron Collider. The circumference is 16.5 miles around. The depth is 330 feet underground. That's mainly just to stop radiation. And it's located at CERN in Geneva, Switzerland, on the Swiss-French border. So part of the accelerator's in France, parts in Switzerland. It's an easy 10-minute drive from the Geneva airport. There are 4 experimental areas, and as I already said, the collision energy is currently 7 TeV, 3.5 on 3.5, and after a shutdown in 2012, the ultimate energy will be 14 TeV. Okay, now the experiment I work on is called ATLAS. It's quite big. You can see the 2 circles I drew with the green blobs. Those are people. So the size of this experiment is roughly 5.5 stories high. It's really very large. There are about 3,000 scientists and engineers who've worked on ATLAS, and that includes about 700 students. The role that Berkeley and LBL, because the Berkeley and LBL groups really function together in ATLAS, is actually building the thing that's at the very center of the detector. It's a pixel detector that consists of 80 million channels of 50 micron by 500 micron pixels, each of which with its own channel of analog electronics. And both the construction of that large pixel detector and the design of the electronics was something that was technically very challenging. The need to go to these pixel detectors is both because they're a very large number of particles, so you need a very segmented detector, and also they need to be very radiation hard because this is a very hot environment from the interacting beams. And by having a very small size of the detector, you can live with a much higher level of radiation than you could for a large detector because you have a smaller capacitance and hence smaller noise. Okay, so what might we find at the LHC? Well, there's a long list here which I'll go to in detail, and this list actually is only the possibilities that are the most obvious. The thing about a detector at the LHC is in many ways it's not really a detector, it's a facility. So when you talk about something like the Hubble telescope, you don't say, what's the one measurement you're going to make with the Hubble telescope? Hubble is a facility that will do lots of different physics. Different people will use it to do the physics they're most excited about, and the same is true of the big detectors at the the LHC. They'll do a wide variety of physics. The one difference is rather than pointing the telescope in one direction, we try and take all of our data together. We divvy up the bandwidth, what we write to tape, and take the most interesting events, and as a collaboration, we argue and decide exactly which events out of the many we could select, we actually write out to tape and analyze afterwards. Okay, so what's the first physics quest from the LHC? Well, it's the infinite search for the Higgs, the particle that in the standard model gives everything else its mass. We believe that the masses of all the elementary particles are generated dynamically through interactions. In the simplest model, this is done by a new particle, which is a spin zero particle called the Higgs. I've drawn at the bottom just a picture of what the interactions of the Higgs looks like with particles, so it gives everything else mass through its own interactions with the particle. Now, my condensed matter colleagues will point out quite rightly that you don't need to have a new scalar particle that's a fundamental particle in order to have a mechanism like this. You could very well have a composite particle instead, something that's made of things we know, and then there are alternatives to the standard model, where rather than having a fundamental Higgs, you might have, for example, a condensate consisting of a quark-antiquark pair that plays the same role in forcing the other particles to gain mass. We don't know which of those theories is correct. However, what we do know is something has to happen on the scale of 100 to 1,000 GeV, because if there's no new phenomenon at that scale, then the calculations that we do basically blow up. We end up having infinities in the calculation. So while we don't know exactly what's playing that role in the theory, we know the mass range in which it has to happen, and the precision measurements we have so far tell us that that mass range should be quite accessible at the LHC. So here's an example of a simulated event for what a Higgs candidate might look like in the Atlas detector. This is one of the gold-plated cases where a Higgs decays to two Z particles, one decays to a plus A minus, and I think the other one decays to, that looks like it didn't draw properly. It should be mu plus mu minus. It's a PowerPoint to open office problem. So it's 2 muons and 2 electrons, and events like that would be very easy to reconstruct in the LHC, but they're also very rare, hence the fact that we need lots of data before we're sensitive to a signal like the Higgs. Okay, the second thing one might find at the LHC are new particles and new interactions, and the poster child for this is a theory called supersymmetry, which is actually a class of theories because there are many variants of this. And this, the space-time structure of the universe is actually expanded to include a new symmetry, and that new symmetry gives each particle we know about a sister or brother particle that spin differs from its own by half a unit. Now, this idea of having a symmetry that doubles the number of particles isn't new. We knew about electrons for a long time before we knew about positrons, and the positron could be predicted when you went to relativistic quantum mechanics, and that was the first example of doubling the number of particles, and supersymmetry does basically a similar thing. So one of the things about supersymmetry is in most of the versions we know about, it has a symmetry associated with it that makes the lightest of the supersymmetric particles, which we call the LSP, lightest supersymmetric particle, stable, because it carries that symmetry and therefore it can't decay into anything else. So that stable particle, which we know must be neutral because if it was charged, we'd see it in astrophysical observations, escapes without being seen, and therefore the way we know it exists, if we have such particles, it gives us a momentum imbalance in our detector. So what you see on the right is, again, a simulated event from Atlas that shows what one of these events in supersymmetry might look like. And you can see a whole bunch of particles going down, a whole bunch of particles to the right, and nothing recoiling against it. We have a very hermetic detector that looks at both charged and neutral particles. So if we see nothing recoiling against these things, that means something's escaped from our detector. Now, it might be a neutrino, but you can calculate all the sources of neutrinos, and the idea is to look for these lighter supersymmetric particles by seeing an excess of events with no balance. Now, one of the reasons that supersymmetry looks like such an exciting theory is the fact that if supersymmetry exists, this lighter supersymmetric candidate would be a candidate for dark matter. Now, I'm not going to try and tell you whether it's 23 or 27% of the universe that's dark matter. My colleagues here have a much better way of arguing that than I can, but they all agree that there is dark matter in the universe, and we don't know what that is, but the one real possibility is that supersymmetry would be the source of that dark matter. Okay. So the third question I want to talk about is the most speculative, but if it happened to be true, would be the most exciting, and that's the question of whether there are extra dimensions. So we all know there are 3 space and 1 time dimension, but that's only the large dimensions that we see. In string theory, people believe there are 10 or 11 dimensions, and the question is what happened to the rest of them, and the idea is, well, they might curl up and be very small. Now, they could be so small that you can only see them on the scale where gravity gets strong, the Planck scale, but there's nothing experimentally that prevents them to be much larger than that. And in these cases where they're larger, then by looking at smaller and smaller distances, higher energies, it might be possible to actually see effects due to those extra dimensions. And in fact, in the most extreme of these theories, it might be possible to produce mini black holes at the LHC, because one of the symptoms of these theories is that gravity becomes strong on a smaller time scale than we would have expected. Now, I have to say that it's very unlikely that you will see many black holes at the LHC, but this is in the category of very high risk, high gain science. The nice thing is we can do it at the same time we're doing the more bread and butter stuff. So this is certainly something that we will look for, although I can't say that I would be putting any bets on our being able to see it. Okay, so the next question is how long will it take? Well, that depends on the nature of the science. We don't know what we're going to find, so it's very difficult to know whether we'll find it quickly or find it slowly, but we can ask based on what observations have already been done at the Tevatron where we might have some sensitivity. So the first thing to know is CERN's planning to run for the next 18 to 24 months at this energy of 7 TeV. At the end of that time, we will have collected 1 inverse picobarn one inverse femtobarn worth of data, and at that point they'll shut down for about a year for machine upgrades and come back at the 14 TeV of energy. So the question is, what will we be able to do with this 2 years of 7 TeV worth of data? Well, in case of supersymmetry, the current limits on supersymmetric particles are about 400 GeV of mass. We should be able to double that to 800 GeV or see evidence of supersymmetry if the particles weigh less than that. In the case of extra dimensions, the increase would be from about 1 TeV to 2, so again, a doubling. The Higgs is a little bit harder. There's a small window around 160 GeV where if the Higgs is there, we'd have a chance of seeing it. If the Higgs is in where it's more likely to be, which is lighter than that, then there will be some hints of it, but it's likely to require 14 TeV of running before there's an unambiguous discovery. Okay, but these models, of course, are only some of the possibilities. The important thing to remember is that the LHC is a powerful microscope. It allows us to explore matter at the smallest distances, tell us whether there are worlds within worlds. After all, we don't even know if there's compositeness underneath the quarks. And the LHC is a time machine that allows us to reproduce conditions of the early universe. So what we have here is an exciting journey, and we don't know what we're going to find, and at least for me, that's one of the reasons that it's so exciting.
I want to make sure that I thank the various organizers of this panel, so including Professors Donghai Li and Chu, and my counterpart, Professor Bangfen Zhu. I definitely want to thank President Gu and Chancellor Birgeneau for creating this possibility, and thank all the panelists. And with that, join us outside.